Here is a valid sequent that we cannot prove with the rules that we've so far looked at. We have two conditionals as our first two premises, if P then Q, and if Q then R, and the third premise is not R. So these are our three assumptions. And what we're trying to prove is it's not the case that P. Well, to do this we use the last of the primitive rules of proof, which is called reductio ad absurdum, RAA for short. And RAA is another of the rules that requires us to make an assumption, but we make an assumption for a very different reason than when we're doing arrow introduction. When we're doing arrow introduction, we assume the antecedent of the conditional we want to prove. But here we're not trying to prove a conditional, we're trying to prove a negation. And so with reductio, the first thing you do is you assume the denial of what you want to prove. So we want to prove not P, so we assume P. P is the denial of not P, and that's an assumption for reductio ad absurdum. We treat it like any assumption. The next step is to prove any two sentences that are denials. That's to say, denials of each other. And here we can do so rather easily. So from P we can prove Q. Here's the conditional if P then Q. Here's its antecedent P. So 1 for arrow elimination gives us Q. And Q is the antecedent of the conditional on line 2, and so we can prove its consequent R from 2, 5 arrow elimination. And now we've accomplished step 2 of reductio. On line 4 we assume the denial of what you want to prove, and now we do have two sentences that are denials of each other, namely 3 and 6. We cite these two line numbers, 3 and 6, and the rule reductio, and then we discharge the assumption on 4 by denying it. So the last step of reductio is to discharge, like we do with arrow introduction, but we discharge by proving the denial of the sentence assumed in step 1. And we cite the two sentences from step 2. And the logic of this is, here we assume P. We show that if P was true, Q would be true, and if Q was true, R would be true. And then we point out that R can't be true if 3 is true. So 3 rests upon itself, 6 rests upon 1, 2, and 4. If all those assumptions were true, if 1, 2, 3, and 4 was true, R would have to be true and false. And if 3 is true, not R is true. But if 1, 2, and 4 are true, R is true. So 1, 2, 3, and 4 cannot all be true. If they were, R would have to be true and false. And that's not possible in logic. So we must reject one of these assumptions. 1, 2, 3, and 4. Well, we stick with 1, 2, and 3. Those are our premises. And so we deny 4. Instead of P, we assert not P. And we say, look, P cannot be true. Why not? Because if P was true, as line 4 assumes, then Q would be true and R would be true. But R can't be true according to 3. So if we're going to stick with our premises 1, 2, and 3, we must reject our reductio assumption 4, and we reject it by denying it. So we've assumed the denial of what we wanted to prove. We've proved, or had available to us, two sentences that are denials of each other, and so we reject the reductio assumption. We deny it. We say, no, it cannot be the case that P. Because if it were the case that P, a sentence, namely R, would have to be true and false. And that isn't possible. And that is the last of the primitive rules of proof, reductio ad absurdum.